Let me on the recording also. And the last class, in the last class, we have discussed, we have started about the instrument transformer, and the instrument transformer, this CT and VT we are discussing. Yesterday we have discussed about that. So any doubt so far, or we can continue the discussion? Please let me know if any query, or otherwise we'll move forward. So let us quickly revise the discussions. So as we know that, let me take the service station. Let me take the side picture of the service stations, because that is the reference of the discussion. So if we take any side picture, so after the surge arrestor, the next equipment that we use in a service station, this equipment, as you can see here, this is the first equipment we can see. When we see from the transmission line, incomer or outgoing transmission line, or let us take the incomer transmission line. So the first equipment this we use, and this equipment we called as the surge arrestor or lightning arrestor, and this is the second equipment or the next equipment after the surge arrestor, and this equipment we call as the capacitive voltage transformer, CVT. So this equipment we have taken, this capacitive voltage transformer, and uh, we are discussing overall about the transformer. So not only the voltage transformer or the capacitive voltage transformer, we have this we are discussing about overall type of the transformer, the instrument transformer, because this comes under the instrument transformer. So this transformer we can divide into three part, as already we know. The transformer, this we can divide into three part. First is the, just quickly revise the study discussion, the distribution transformer. Second type of the transformer is the power transformer, this we know. And third type of the transformer is the instrument transformer. The distribution transformer rating comes into the kVA, the power transformer rating comes into the MVA, and when we talk about the instrument transformer, this rating comes into the VA. That is this rating comes of the instrument transformer. This instrument transformer used to feed supply our input to the meters and to the relay. So this meter burden, or the required power to this meter and the relay is because this is made by the power electronics instrument, so the required power is less. So that is why this rating comes into the VA. So again we have to calculate the VA ratings also. So in the transformer, this kVA rating you will calculate or select separately. This VA MBA rating we will discuss separately in the next module number 3, and at present we are discussing this VA rating calculations. So this instrument transformer we have taken, and this instrument transformer we are discussing, we can say the selection and the sizing of this instrument transformer. So this instrument transformer we divide in again two part. One is the current transformer and second is the voltage transformer. And we discuss a study that this current and voltage transformer is not the current and voltage measuring device. This is just like a power system transducer. We can see that they are scaling down the current and voltage from HV system and feeding the less voltage and current to the connected meters and the instrument and the relay. So they are only scaling down the current and voltage. That is our study discussion. And second, at the same time they are providing the isolation between the HV part and the LV part, between the high voltage primary circuit and to the and isolation between the connected instrument meters. We can see meters are, we can see the productive release. So this these two things we have discussed yesterday. Now uh, we have taken this CT, and we started the CT selection and sizing calculations. So this current transformer we again divide into the two part basically. One is the metering, one for the metering purpose. We use the current transformer to meter how much current is flowing, and second we use current transformer for the overcurrent at fault, or we can say the protection purpose. So this metering CT now we are discussing, right? Yesterday we have discussed about this metering CT, and yesterday also we discussed that in the substation, or in case of substation or switchyard, we use the multi ratio. We use the multi ratio and the multi-core CT. This we use. So why multi-ratio is required? Because when we are making any switchyard, the expected life is the next 30 or 35 years, we can say. So initially the current flowing is less. Initially the loading on the substation is less, so that we can use the lower tapping ratio. And when the CT, or when the plant, or when the transformer is running on the full capacity, so we can go to the higher CT ratio. So to get the accurate to get the accuracy in the metering and the protections, this when the less are light load conditions in the initial years of the substations, this multi ratio is useful. And now when it comes to the multi-core CT, so why we use? Because we have more than one function in this current transformer, as just one second. We have more than one function required. So in place of using two, three, or four different CT unit, just one second. Soumya, please mute yourself. So multi-core CT, because why we use the multi-core CT? Because we require more than one function from the CT. So in that case, in place of using two, three, or four different CT unit, we use the single CT. We use the single CT, and we have one common primary, and at the secondary time we use the multi secondary winding, 2 3 4 5 secondary winding we can use. So this is called as the multi-core CT. So one winding we can use for the one purpose, say we are connecting the emitter here, and second winding we can use for this another function, say we can connect any overcurrent relay. Third winding we can use for the another person, suppose we are putting any other relay, suppose differential relay or any other relay. So to get this kind of the facility, we use the multi-core CT. And when we talk about the CT sizing, basically we are not doing the CT sizing, we are doing the core sizing. We are doing this core sizing because each core have the different applications. So each core we have to do uh, for each core we have to do the selection and the sizing calculation or the rating calculations. This core may have different, because this core is altogether different from this core. So this core we can define with this different characteristics. This core we can define, we can manufacture, or we can define with the different characteristics. This core we can define with the different characteristics. It is possible because this core is not is separate. This all cores is separate from each other. So we are doing the core sizing or core selection and sizing calculations when we are telling about the CT sizing calculations. Sometimes this is called as the core dimensioning. Sometimes the same point we call as the core dimensioning. So sometimes in the CT sizing calculations, Excel sheet or the calculations document, we write at the core dimensioning calculations. That statement is also correct. I hope this is so far it is clear. So far it is clear, and we can move to the next discussions. So we have taken the metering core CT. We have taken this metering core CT. So let us make a bus bar, and then it is going to suppose any transformer or any motor, anything we can say, putting a circuit breaker to control this transformer, and now we are putting the CT core. CT core. So this CT core, three CT core, suppose we are putting one CT core metering and second for the protection purpose. So for this metering CT core, what parameters we have to specify? So the first parameters we have to specify, that is the CTR, current transformation ratio, that calculation yesterday we have discussed. The second parameters we have to specify for this metering core. For this metering core, suppose this is the metering core, and we will come later on about the protection core. First, let us discuss about the metering core. Second parameters we have to specify about the accuracy class. Accuracy class, this we have to specify class of accuracy. Third parameters is their output VA burden, and the fourth parameters is the instrument security factor. So these four parameters we have to specify for this metering CT core. So this one first parameters already we have discussed. Now coming at the next parameters, accuracy class. Accuracy class. Accuracy class means what? When we are taking the CT, when we are taking the CT, let us take one to understand the accuracy class. Let us take a CT circuit. So in the CT secondary side, as primary side, as we discussed yesterday, we take 1 tons or the 2 tons. This is primary side. At the same time, on the CT secondary side, we have multi tons, we have many tons, we have many tons, and now it is, we have here the output terminal of the CT, and this output terminal, now suppose we are connecting to any multifunction meter or any MFF or energy meter we can take, or emitter also we can take, right? And then it is connecting to this CT secondary, S1 or S2 that we can put here, and here we have the P1, and here we can write as the P2. So when the current is flowing in the primary, the same current based on the transformation ratio, based on the number of turns, it will come here, and the current when it is coming on the secondary side, we can say the IS. So some part of the current will go to this core excitation, or we can see the core magnetization. I mean to say, please try to understand, and if it is clear, so please let me know CL or CC, uh, so that it is, we confirm that you got the point. So suppose we are taking 1,000 or 100, say 100 by 1 ampere CT. It means when the 100 ampere flowing in the primary side, then secondary side 1 ampere should come. But this is my rating. This is my rating. Same we have mentioned on the CT rating plate also. This rating and same mention on the CT rating plate also. When I'm telling the rating plate, it means to say, let me take any rating plate. Let me take any rating plate. Yeah, thank you, Raghunath Sanat, because if you are getting the point, so please be active on the chat box so that we can fast forward the discussion. Let me take where I have just wanted to say to show CT. Yesterday we have seen one side picture about the CT, yeah, ring type CT. No, that is not clear. That is not clear. S2, S1. So this S1, S2 we have marked like here. S1, S2. Okay. This is my rating plate. Let me take any other. Let me take any other. Any other instrument. Yeah, this one we can say. Yeah, so when I'm telling the rating plate, is it means this is my CT that we can see here, and now this white label you can see on this CT, it is the rating plate. So this is my ratio, means this is my current ratio to 100 by 5, burden and class. So we had this ratio already we have discussed and we have done the calculations. So coming at the next parameters, burden and the class. So burden we will go later on. Let us discuss about the accuracy class 0.2s, and this is the 200 by 5 ampere ratio CT. It means when the primary current 200 ampere flowing, then secondary side 5 ampere current will should come. But what will happen due to the uh, excitations current, due to the magnetization current, we can say the IM, we can say, or we sometimes write as the IE also, some amount of, so this is, let us take 200 by 5 ampere CT. So when the primary side 200 ampere current is flowing, ideally ideally 5 ampere current should come here. But what will happen, some part of the current from the 5 ampere, it will go to this to magnetize this CT windings. So due to that subtraction, due to that magnetization current and excitation current, the rated the rated the rated the actual transformation ratio will not be equal to rated transformation ratio. I again repeat my statement. Due to the magnetization or excitation current component, the actual current transformation ratio will not be equal to rated current transformation ratio. And due to this mismatch, or we can say due to this error, due to this due to this excitation current or magnetization current, the error will produce in the CT, and that percentage of the error we express as the accuracy class. It means it means when my accuracy class say zero point 0.1 zero point 0.2, it means 0.2 percentage, 0.2 percentage error. If I mention here 1, it means 1 percentage of the error. So 0.2 is less compared to 1. Right now, it means 0.2 class CT is more accurate compared to class 1 CT. It means 0.2 class CT will be more costly because they are using the better material, better winding materials to minimize the error. It means 0.2 class CT will be more costly than the class 1 CT. So this error we express in the terms of the accuracy class CL. So first of all, we should understand the significance, the basic meaning of the statement, and after that we will go to the selection and the calculations. So first of all, the basic significance. So CTR is the done, CTR is done, and I hope the accuracy class is also clear. What is the actual and the basic meaning of the accuracy class, right? I think please be active on the chat box. Yeah, you just you just active CL or anything. I'm coming on that. I'll coming on that. Admit, please follow me, and I'm going from scratch to the advance. So let us go step wise, and it will take more time. But let us keep this whole training session is your complete training session, so that after this session, no need to take the training on the electrical system designing. Okay, so I'm just trying to these things that in that we understand all the electrical industrial concept, so that everything should cover here, right? So yeah, accuracy class word is clear, accuracy class word is clear, accuracy class word is clear, and forget about the point 2 s at present, but point 2 is clear. I'll come on the s, I'll come on the s, but point 2 is clear. Okay, so that is clear. Yeah, correct, Raghunath. Now this is the accuracy class we understood. So now the accuracy class or maximum allowable error is, we need to select, please focus, please concentrate. The actual allowable error are error means accuracy class. So if I'm telling error accuracy class, you need to understood that is the error, right? As we discussed here. So The actual accuracy class selection will depend on the application of the CT, that where I am going to connect. I mean to say, if I am connecting this CT for the revenue metering, for the tariff metering, for the power generation metering, for the power selling purpose metering, for the tariff metering purpose. In that case, we need to select the higher accurate CT, the higher accurate CT. And suppose we are using the CT not for the revenue, not for the tariff, not for the energy billing purpose, just for the information purpose. So we can go with the little bit higher error, right? So this accuracy class we need to select based on the where for which applications we are putting the CT. Please understood. This we need to select based on the applications of the current transformer, and in the current transformer IEC standard. In the current transformer standard means we are referring the IEC standard. What is the available accuracy class? What is the available accuracy class that available rating is given? So selection is the application wise, and but we should know that what is the range available for the selections. So that accuracy class we will go with the IEC, and we can see that as per the IEC what type of the accuracy classes available are as are um, recommended as per the IEC. So for that we can go to the IEC 61869, IEC 61869, and I think I have taken the snapshot also. So yes, let me take this metering city we are taking, and this is the available accuracy class zero point 0.1, 0.2, 0.2. Yes, and this informations I have taken from the IEC standard. And this we discussed that for the CT metering city, these four parameters we have to look. CT ratio already we have done. 1 and 5 ampere already yesterday as we have discussed. Now coming on the accuracy class selection. So as per the IEC 61869 part number 2, page number 21, clause number 5.6, the standard accuracy classes for measuring current transformer are 0.1, 0.2, 0.2s, 0.5, 0.5s, 1, 3 and 5. This is my available accuracy class as per the IEC standard. Now as a design engineer we should understand that where I will take 5, where I will take zero point 0.1. So as about this study we have discussed that 3 and 5 generally nowadays we do not take class 0.1, 0.1 class we take for the lab purpose, and from 0.2 to class 1 that we take in the industry. And now if we come on the selection purpose, so this let me take this now. I just wanted to take, yes. So 3 and 5, let me delete from here. 0 point, this is all my available accuracy class first of all. And now we have to select the accuracy class based two parameters, that what is available as per the IC, and now based on the applications we will select applicable. So if my CT I am putting for the lab applications for the any laboratory, in that case we take 0.1 class CT, very less error we take. 3 and 5 we do not take. And when it comes to the low voltage, when it comes to LT, low voltage is I'm telling means 220 voltage, 415 voltage or 400 voltage. This is my low voltage range. R for medium voltage, class 1 CT we can use. LT for sure class 1 CT we use, right? And for the medium voltage class 1 CT we can use, or we can use 0.5 to 0.5 as. So for the medium voltage and high voltage CT, 0.5 and 0.5 as we select. And when it comes to the extra high voltage or ultra high voltage we can say, in that case 0.2 or 0.2 s class, s class S, accuracy class CT we use. So this is one kind of the selection based on the voltage, based on the voltage. Similarly, we have some other selections also based on the other applications also. So that we can see here. For the ammeters in the LT class 1, for the 415 voltage feeder energy meters, non-energy meters, 0.5 also we can use, even though this is LT, but if we are going for the energy metering, 0.5, yes, that also we can use. For the energy audit meters like the station transformer, unit auxiliary transformer, incomers, 6.6 kilovoltage, 11 kilovoltage motor feeders, 415 transformer feeders, incomer feeder, even though this is LT, but yes, because we required higher accuracy, in that case 0.5 S accuracy class CT we can use. For the non-ABT, ABT stands for the availability based tariff meter. So this ABT is the tariff meter or the revenue meter, revenue energy meter. This ABT meter we use in case of the solar, in case of the hydro, wind, or anywhere where we are doing the power selling, where we are doing the power purchase or power selling. So in that applications, for that we use the ABT meter, availability based tariff meter. That is the full form of this ABT meter. So for the non-ABT region meters, non-ABT means there is no any revenue metering, in that case zero point 0.2 we use. And when it comes to the energy metering, and when it comes to the line meters, generator meters, generator transformer, station transformer, UAT, HT site emitters, for all these applications we prefer to use 0.2 S class CT. So this is a criteria for selection as per the statutory requirement. So 2 point we discuss here as per the voltage, plus we discuss as per the requirement, as per the statutory requirement also. I hope this accuracy class selection is clear to everyone. And now we can discuss here the difference between zero point 0.2 and zero point 0.2 s, 0.5 and 0.5 s. And that is very important point, because during interview this is a kind of the favorite questions, that what the difference between zero point 0.2 and zero point 0.2 s class CT and 0.5 and 0.5 s class CT. Anyone have the idea about this, the difference between zero point 0.2 and zero point 0.2 s? What is the s meaning here? Yeah, thank you, Raghunath. Yeah, anyone have the any basic, idea the difference between zero point 0.2 s, zero point 0.2 and zero point 0.2 s? Correct, that is the special class, Rahmatullah. That is the point number one. Any other point? Any other point anyone can add the difference between point? Yes, sure. You can. Yeah, I'm waiting just for the reply. Yeah, so the difference between zero point 0.2 and zero point 0.2 s class CT. Okay, let us correct, accurate even at low current. So let us take the IC again. Let us take the IC again, and based on the IC, let us discuss the difference between zero point 0.2 and zero point 0.2 s class CT. So when we go to the IEC again 61869, because that is the IC for the current transformer. In that case, now we have to go to the table number 201 and table number 202, and IEC 61869 part number 2, page number 21 and page number 22. So as per the IC accuracy class that we can see here, that is the ratio error and the phase displacement, because there's two error comes, the current ratio error and the current phase displacement. So this all 0.2 and 0.2 is what we are discussing, that is the current ratio error, and the phase displacement error that we can see separately here, that we can see separately here. So based on the current ratio error, the allowable phase displacement error is mentioned in the IC, so the manufacturer have to follow this allowable phase displacement error. So we are discussing about the current ratio error when it comes to here, and we can see the accuracy class point from point 1 to 0.2, 0.51, because 3 and 5 generally we less use, 0.2s and 0.5s here. So let us try to understand this IEC snapshot, 6.69. At current percentage of the rated. Please try to understand. 5% of rated current. This 5 means 5% of the rated current. What does mean 5% of the rated current? Means my CT is there. My CT is 200 bar 1. Sorry, 200 by 5. 5% current is flowing. It means how much? Only 10 ampere current is flowing, right? Am I correct? Right now, if the 5% current is flowing, because what will happen when we are putting the CT here? When we're putting the CT here, it is not mandatory. Suppose this is my 5 MVA power transformer, 5 MVA power transformer, 6.6 by 415 voltage that we have considered here. So in that case, it is not mandatory that this transformer will be on every time 5 MVA full load. There might be less load, there might be 50% load, there might be 100% of 5 MVA load. So suppose the light load conditions come, the light load conditions comes, any like big motors we have taken, any large motor, and that we switch off, that or we have taken out of service for the maintenance purpose. Suppose in that case this transformer will be under light load conditions, and suppose the less amount of the current is flowing through this power circuit. So that how much amount, suppose it is flowing only the 5% of the current. In that case, if we take the 0.1 accuracy class CT, even though zero point 0.1 accuracy class CT we have taken, but it will not guarantee 0.1 percentage error. 0.1 percentage of accuracy class is guaranteed when the 100% current is flowing. Means whatever the CT we are using, whatever the this CTR we have done a calculation in the study, and the CTR we have taken 500 by 1 ampere CT. 500 by 1 ampere. That is study we have done the calculations. It means when the 500 ampere current flowing in the primary, and then in that case this will produce 0.1 percentage of the error. But at the same time, if the 5% or 20% current is flowing, then the same CT accuracy, the same CT core will generate more error, and that will generate 0.4 and 0.2 percentage of the error. So error is increased. When it comes to 0.2, and that we can see here, 5, 20, 100, 120. 0.2% is guaranteed only for the 100 and 120% of the current. But at the same time, if the current is less than 100, means 20, then it will 0.2 accuracy class CT will generate 0.35% of the error. Means your error is increased. And if 5% of current is flowing, then 0.75%. It means your error again increased from 0.2 to 0.75. Right? At the same time, let us take 0.2s, and that we can see here 0.2s. So what the major difference that what we observe? First of all, the 0.2s class CT, even though they can measure the 1% of the current, and that 0.2 cannot measure, right? Means at the 1% of current there is no any IC error indicated. Means the manufacturer cannot take the guarantee, he will refer this IC. But 0.2s class, they can measure the 1% of the current also. So that is my one requirement, and that is the one difference between the 0.2 and 0.2s class CT. So if we make the point for the interview purpose, and if we make the point for the interview purpose, and we take two accuracy class CT, zero point 0.2 and 0.2, stand for the special, no doubt in that. So what is the special in that? 0.2 class CT, 0.2 class CT cannot measure the 1% of the full load current, but they cannot measure 1%, they cannot measure. But yes, 0.2 s class CT, they can measure the 1% of the current also, right? They can, but yeah, at the same time error is higher, but yes, they can measure. So that is the difference number one. The difference number two, so we can put the dash here. Okay, the difference number two is that the 0.2 class CT, as we have seen here, the 0.2 class CT, the 0.2 class CT is defined, is provide the 0.2 percentage of error when current is 100 and 120 percentage of the primary current, right? So this is the one difference. At 5% 0.75, 20 0.35, but when it comes to 0.2s we can see at 5 percentage it is producing less error 0.35. Here at the 5 percentage of the rated current it is producing 0.75. It means the 0.2 S class CT is more accurate, compared to zero point 0.2 class CT, even in the low CT current, in the low amount of the current, in the lower current. The 0.2 S classicity is more accurate than the 0.2 classicity. So that is the one statement that I can write here. The second statement that we can write here, that 0.2 S classicity is more accurate, is more accurate accurate compared to 0.2 S classicity. Compared to, you can write this statement because it is taking compared to 0.2 classicity. And that we can see third major difference is that zero point 0.2 class it is 0.2 percentage of the error from 100 to 120 percentage of the full load current. But at the same time, if we see the 0.2 s class CT, their range is not 100 and 120, their range is 20 to 120 percentage, and from 20 to 120 percentage they are offering 0.2 percentage of the error, where at the 20 percentage they are 0.35 percentage of the error. So we can see the next difference, that 0.2 class cities, of they will they will produce the error 0.2 percentage at 100 and 120 percentage of the full load current, primary full load current. But at the same time, 0.2 s class CT will produce 0.2 percentage of the current error from this 20 to 120 percentage of the range. So see, 0.2 s class CT is more accurate in the lower amount of the current compared to 0.2 class CT. I hope this three statement is making us clear about the difference between 0.2 and 0.2 s class CT. The same concept we can apply to discuss to understand about the difference between 0.5 and 0.5 s class CT. Same concept we need to apply here. I think now your query is addressed at who asked me about this query. Yeah, clear right now. Your query is clear. Yeah. Okay. So we understood here. We understood here. Accuracy class. Please delete this line. Yeah. So we understood 2 points here. First of all, now we are discussing about the 4 parameters in the accuracy in the CT. Specific is in the CT metering code accuracy class. So the selection of the as per the IC, this is the available this is the available range of the accuracy class. The selection based on the voltage and based on the applications, and that we discussed, and I hope this is clear to everyone. And the next point we discuss about the uh, difference between 0.2 and 0.2 s class. Now let me ask you, uh, can anyone tell me, discussion, this is the discussion as per the IC, but can anyone tell me as per the applications where I need to put 0.2 and when I need to take 0.2 s class CT? And can we can say here that for the substation why we take 0.2 s class CT? Is it clear now that for the substations why we need to take 0.2 s class CT? I think this statement is clear because we first of all we required the better accuracy, and second, my current is not every time 100 120 percentage. My load will fluctuate. So 20 to 120 percentage, if my current is vary initially 20 percentage suppose, and then 50 or 100 percentage, then we can have the same amount of the accuracy. So my statement is that for the substations we always take 0.2 s class CT. This is the one statement, and I think no one have any doubt in that statement. Now when it comes to the application wise, let us take some industrial applications and we try to understand where point 2s classicity. So if let us take any solar power plant, any wind power plant. So in the solar and wind power plant, when we uh, at the place of the transmission line, uh, the power evacuated line, we need to take point 2s classicity so that we can have the better current measurement, right? Okay, so second parameter is clear. Second accuracy class selection is accuracy class is clear. Now let us come on the third parameters for this CT metering core, VA burden. VA burden means what and how to, and as we discussed yesterday that out of these four parameters, this CTR and the VA as per the calculations formula, and accuracy class and ISF as per the IEC, and as per the applications we need to select, or as per the statutory requirement we need to select. Okay, class and the IC, these two as per the calculations. So let us come on the third parameters for this metering core, and that is the VA burden. That is the VA. What is the meaning of VA? The meaning in the layman language, in a basic language, what is the meaning of VA? VA means power. Am I correct? Right, power we express into the kVA, MVA, or VA. First of all, the VA is clear, that is the power. Power means what? When we are taking the CT, and on this CT secondary side, we are putting some load or some emitters, we can say anything, or any multiple emitter, or any instrument we are connecting. So that, and here we have the cable, here we have interconnecting cables, and that is connecting this cable have also some resistance, and it is connecting to one external meters, in external meters. So this CT core must be suitably select so that they can produce the required power to flow the current. That is the one way we can express the VA. The same times VA also called as the burden, means on the CT secondary side how much burden we are putting. So burden means the burden of the cable and burden of this meter, and this CTVA should be more than the connected burden. Okay, so VA stand for the power, how much power they need to produce on the secondary side of the current transformer. And now this power we need to calculate, and we know the formula that VA we can express into the another terms also. V stand for the, because we are not aware, we can rewrite this VA value. V is equals to IR, right? And A means the ampere we can write as the I also. So the VA we can rewrite as the I square into R. It means we will take that how much current is flowing through the cable. So that current 1 ampere obviously, so we can take 1 square and we can take the R. So this current here, and now it is coming back to this. So this is in the one direction, and now coming back in the reverse. So again we need to add 1 square into R, or we can write here I square into R, means I square into 2RL, means it is going and coming back to the CT. So I square into 2RL, this is the required power or required burden of this cable, and plus this instrument we are connecting on the CT. So we have to take this instrument burden. So what we do, we do not for this instrument, for this metering instrument, we do not go with this formula. We need to go with the instrument catalog, because this instrument is manufactured and provided by the any different vendor. So we can go to the instrument catalog, and from that catalog we can see that how much power required to this ammeter, and our power required to that energy meter, and that power value we can put here, that power of the external VA, the power of this ammeter or multifunction meter energy meter we can add here. So we can add this power in this formula, and plus we can add this external instrument power, and we can add both the power, and we can calculate that how much burden connected at the CT secondary site. So the CT burden should be more than the connected burden. I hope this is clear and that this is making the sense. Yeah. So how we can calculate that? How we can calculate that? Let me see if I have any instrument. Where I have the instrument? This. Give me one moment and let me search out the catalog first of all. Give me one moment. Yeah. CT, 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 CT. Yeah. BCU. Okay, that we can see here. BCU, but I do not want it to BCU. Let me take any. Yes, Raghunath. Burden. See, Raghunath. Every core have the different calculations. Okay, so every core have the different burden. May have different burden. So burden calculated for each core. Yes, and suppose and each core the connected instrument is same. If the connected instrument is same, in that case no need to calculate, but if the connected instrument is not same, in that case we need to calculate for each core. Okay, Raghunath. Yeah, so let me take any multifunction meter, this where I have this multifunction meter. Just give me one moment, yeah, because before the class I put the reference document, but sometimes some document is instrument for class, and I need to, yeah, input, correct, yeah, and I found here, yeah, that we can take here. So this is the energy meter, this energy. So this is suppose Recep make energy meter. Recep is the instrument manufacturer, the energy meter manufacturer. EM energy meter 3940 model, kilowatt hour energy meter with the RS485 communications. So we can configure the same instrument on the DCS or PLC or SCADA also, because we have the communications put available in this energy meter, right? So yes, so we are doing the calculation for the burden, for the burdens. We will take the Excel sheet for the calculation, but since this calculation is very easy, so no need to go with the Excel, we can do manually calculations also. Yeah, so we are doing the burden calculations, the VA calculations. So the formula, let us put the formula to calculate the burden. To calculate the burden, VA, VA is the S square. Let me put the secondary current in place of IS square into 2RL cable lead go and through. I hope this is clear to everyone. Same we have done here. VA, VI square into R, IS square into RL. Why 2RL? Because cable is going and coming back. So one length for the here and second length for this. So R plus R2R. L stand for the lead. This is my cable lead. Or we can remove L, no important. We can see C also, cable resistance. Okay. Yeah. Plus all the external instrument burden. Suppose let me correct few other instrument like that. CT secondary here, then cable, then this is cable, and suppose here we have the ammeter, plus here we have the energy meter or any other transducer we are putting here. Whatever the instrument we are putting, we are connecting to the CT. All the instrument in the series we have to add, and then we need to connect this cable. So this cable burden are lead, this is called as the lead, plus the burden of this ammeter, plus this burden of the energy meter. And the burden of ammeter and the energy meter we can check from the catalog of this instrument, we can go to catalog, and from the catalog we can find directly the burden of this instrument, and that we can put here. So this burden plus this burden, suppose we have here the energy meter catalog, and that we can see this is my energy meter catalog. So we can the technical specification, so we have to go to the technical specification of the catalog, and we can see the input voltage. This input voltage is just to power up the instrument. Okay, power up the instrument. So do not, this is not supplied by the CT. This is for that we take the another SMPS or any DC voltage and RAC voltage, and through that we power up this energy meter. But uh, to this energy meter, the input current 1 or 5 ampere AC RMS. Okay, again this is the, so this two input required for the AC auxiliary AC DC sizing calculation, auxiliary supply. So auxiliary supply to power up the instrument. I think you are getting the difference. What I mean to power up right now, to so that if they power up, then they will take the readings. Okay, like we use the cell to power up, so that kind of the things. Okay, and now when it comes to the burden, nominal input voltage burden 0.2 VA approximate per phase. This 2 is the auxiliary supply, and now this is my CTVT supply. Okay, so VA burden, nominal input voltage burden 0.2 VA approximate per phase. So when we are discussing voltage uh, the voltage sizing calculation, the voltage sizing calculations, and in the voltage again we use two type of the voltage transformer: metering voltage transformer to measure the measure the voltage, and second we have the protection voltage transformer. So for the metering voltage transformer core we will take 0.2 VA value. So uh, second second why the voltage and current both is coming, because this is the energy meter. So in the energy meter we require two input, one is the current and second is the voltage, and by the multiplication of voltage and current they will display the energy. So that is why two values given here. So the voltage we will take 0.2 V, and when it comes to the CT, so nominal input current burden, right, 0.6 V approximately per phase, that you can see here. AC supply burden 4 VA. So 3 VA, 3 burden we have. This one go to the AC supply, this one go to the V supply voltage, and this one go to the current supply. So I will take 0.6 VA for the CT sizing. Am I correct? And suppose in the next we will do the VT sizing. So for the VT sizing, the same formula we have to apply, but zero point 0.2 VA we have to mention in that time. Okay, so my uh, ammeter catalog we do not have at the present, so we have the energy meter catalog. And as per the catalog, I am again repeating, as per the catalog, the burden of this energy meter is 0.6. So IS square into 2RL plus 0.6. This value we can take, and IS is the 1 square. Now what about the RL? So RL is my cable resistance. So for that we can go to the cable catalog. And from the cable catalog we need to find out the cable resistance. So here I have taken this polycap make wires and cables, and between the CT to the from CT, let me see the recording. Yeah, from CT to the ammeters, in generally we take 4 square mm cable, right? 4 or 6 square mm cable we take, and in generally we take 4 square mm cable. So I am directly going to the cables technical data, nominal size of the cable, so that is 4 square mm, 4 square mm. And now we need to check here their resistance. So and we take 4 square copper cable, so the resistance of the copper, of the plain copper, is 5.90 ohm per kilometer. I mean to say as per the catalog, 5.90 ohm ohm per kilometer. It means for the 1 kilometer the cable will offer the 5.9 ohm resistance. So now the next exercise we have to do here, we have to take the length from CT to the energy meter, and when we go to the panel, In case of the LT panels or indoor panel, both comes into the same panel. So this cable length is around 2 to 5 meter max to max. But when it comes to the substation, when it comes to switchyard, in that case the energy meter is placed inside the control room building and the CT placed outside. That we can see here. Let me take any side picture. Just equipment. Yeah, that we can see here. So this is my building here. This is my building here, as you can see here. Building, inside the building we are putting the panel, and in that panel we are putting the energy meters. But the CT and PT, all the equipment is placed outdoor. So suppose CT we are putting here. So from this we have to take how much, what is the route available and how much length of cable is coming from CT till this panel. So meter that meter we have to measure, and that length we have to take here for the calculations. And let us take 500 meter, right? For example, so for that we need to check the distance between the CT and in the panel energy meters. Actually, generally we take, suppose the length is not clear at the starting stage, so in that case, in generally we take 500 meters. I am telling this tentative value, but when you are making the layout, electrical layout, in that case we have to measure this value by the AutoCAD. Let me see if I have any AutoCAD drawing. Let me see, and I'll tell you how to measure this. Yeah, I think so far it is clear right now. Any doubt, you can tell me. Ongoing project. So for that we can take let me take whether we have, yeah, I have one AutoCAD. 50 meter is less, Ramatullah. Do not take 50 meter. In case of substance, you go with the 300 or 400 or 500 meter, around that. Okay, so if 30 VA is given as a burden, can we understand? It? It is 30 VA per phase per core. Correct. Per phase, RYB 3 phase we have. So this 30 VA is per phase. First of all, and yes, it is per core. Per core. Okay. Yes, Rahmatullah. Yeah. So that here we can see one AutoCAD of the electrical layout. One AutoCAD electrical layout. Right, and this is my control room building. This you can see here. This is my building here, and here we have placed this all the panels, 220 voltage, AC, DB, LTP. Here we have placed the panels. We'll come on that. Will come in this drawing. Will come later on. And here we have placed some this panels. Test lab. Okay, so now what we need to do, we need to suppose CT we are putting here. CT we are putting here. This we can see, this is my central line of the CT, this one. So we need to use the PL command, power PL. Please consider it at my command line in the AutoCAD. I'm using P and L. PL stand for the polyline. So you enter this command, and now we can draw one polyline. We can draw one line. So from this, let us take this CT here, and now we are going. This is my cable trench. This as we have indicated here. So now I am following my cable tray routing. Okay, this is coming here. This is coming here, SPR. Suppose now in the switchyard also we have switchyard protection room, and suppose it is coming, my relay is placed here, or my energy meter placed in this SPR room. So we can put here, and we can then enter, and this cable, this line we can copy. CO, use this command to copy the line, and we can take outside of this drawing. And now we can go to the quick property, right click and go to the quick property, and now we can see here the length. I think this length we can see here. Or control 1 also we can use, I think. Yeah, control 1 we can use. And then this area length, I think 84207. This length is coming very much, 84 meter. There's something happened here. Something what happens here. Yes, this control 1. Yeah, polyline. 84207 mm divided by 1000. So 84207, this is in the millimeter. Okay, so divide by 1000, right? We can say 84 meter. Am I correct? Right now, because this drawing we made into the mm. So in this 84207, this is in the millimeter. Now convert into the meter. So divide by 1000. Am I correct? 84 meter, right now. Yes, 34 meter. So this is the method how to we calculate the length. Okay, and I'm telling you this is the way that we will do in case of the real project. Or if suppose we are doing the tentative sizing, in that case we can go with the 500 mm, 500 meter we can go, right? So now for 1 kilometer 5.9 ohm. So for the 500 meter, what should it will be? 5.9 divided by 2 ohm, right now around we can say 3 ohm. So generally you can calculate now for the 100 meter how much it will come, for the 84 meter how much it will come. So that is my cable resistance RL. So that we need to put here. So 1 square into 3, because 3 ohm we have calculated here for the half for the 500 millimeter, and plus 0.6. So how much it will be? 1 square into is the 1, so 3 plus 0.6, right now. So 3.06, we can say in that case 3.06 is my required burden, and the CT output burden should be more than 3.06. In that case we can take 5 VACT. I hope this calculation is clear. I can take 5 VACT. This is the method how we need to calculate this burden. You can see burden 5 VA we have taken here. So how to calculate the 5 VA? CTR already done. Accuracy class 0.2s already we have done. But burden, yes, that also we calculated here based on the cable length and based on the external connected instrument burden. External connected instrument burden. Clear? uh, Please let me know if this is clear. Yeah, 3.0 3.6. So we should take some margin also right now. So we can go with the, because 3.6 is not the standard rating, so we can go nearby standard available rating in the market, and 5 we can select here. And we can see also what is the standard VA rating available as per the IC also. Let me check if I have IEC. I have the IEC. Just 1 second. And we can see from the IC equipment, instrument, transformer, and then 61869 CTPT for class. Yeah, CTPT 61869 part number 2. Yes, same screenshot I have taken from this IC. This IC already I have given to all of you. Okay. Yes, so we can see here. Can we see the standard VA burden? Yes, rated output values. The standard values of rated output for measuring classes Class P and class PR are this one 2.5, then 5, then 10, then 15, then 30. So the 5 VA we can take. 8, 7 VA, 8 VA not allowed, 10 VA is available. So 5 or 10 or 15, 30 VA, this is the standard value. Out of that we can select. So my calculation is 3.6, so I am going to the 5 VA. I hope this is clear to everyone. Okay, Raghunath. Same like this, Raghunath, please, everyone active at this. And you need to put C, or CL, anything, so that if you understood, we can increase the speed. Let's say for 2 CT core of the button 15 VA and 30 VA, which physical design parameters and it is. Okay, Silpa, we can have this discussion in the last. Okay, now let me tell one point here. Let me add one point here. I have seen sometimes that in some calculations we also use the CT internal resistance also, because the CT also have, because we are putting the winding here, so the CT winding will also have some resistance, that we can say the CT resistance. So I have seen many times, in order to calculate the burden, the CT burden, some engineers, some company follow this formula. They take is square, and not the 2RL. They take the RCT also, the CT secondary winding winding resistance, and that we can write as the RCT plus 2RL, the cable lead resistance, and plus external plus external burden plus external burden. Okay, so thank you, yeah. And please rename, yeah, 141A. Please rename your name, because some code is coming. Okay, so yeah, is square into RCT plus 2R plus external burden. This some company use this formula also in order to find out the CT burden. But if I 1 second, just 1 second. Just give me one moment. Give me one moment. Yeah, so if we take this definitions, rated value of the secondary connected resistance, resistive burden in the ohm, secondary connected resistive burden, or secondary connected burden, we can say. So actually we are doing the calculations for the rated output of the CT, or how much burden externally we are going to connect. So in my understanding, or when I do the calculations, I do not consider this RCT value, because as per my understanding, we I am taking that how much external burden required by the CT. So this RCT is not the external burden, this RCT is the self burden of this CT. Okay, so that is why I personally do not include this RCT value, but I'm telling both the point. I'm telling my practice, I follow this practice, but yes, I have seen some calculations to that also. There is no any problem in that calculations, we can go. So what the difference will come, I means the 1 square, RCT, the CT resistance burden we have to take. Suppose they have 3 ohm or 4 ohm, whatever 4 ohm or 5 ohm, that we need to take from the city manufacturer, and plus this 2RL means what we are taking, 2 plus 3 into 6, and plus 0.5, that we have done calculations, right? 0.6. So what will happen, this 11 plus 0.6 means 12 ohm, means we have to take the 15 VA burden here. Right now, if I include that, because RCT's value is high, not the less burden, this is high burden, it comes. So 15 VA in that case it is required. But as I said, because this VA is the output power, not the, in that case the internal power, internal resistance we should not include. So I'm telling you the both method, you can go this one or you can go this one, but as per the significance we should go this one. So I have seen few consultant use this formula, and some few Indian consultant use this one formula also. But I'm agree with this formula, so I'm telling you this formula. But yes, this one also, if anyone using, so no need to say that this is wrong. This is also okay, but the CT price will increase. So as a consultant, you don't have any issue, but as a client, as a EPC contractor, you have the issue because the price is going to increase. Okay, so it's better that we follow this one. I hope you have both the understanding. This is your choice. I am telling you both the concept. But if you ask personal my, I will go with this one because this is the output required power. In that case, we do not take the input CT. And actually, I have seen few calculation by some good consultant, some major consultant, in they have used this formula. So that is why in the class I'm telling you this formula. Okay, so client will approve this one also, and client will approve this one also. You go with this one, and you ask that because this is the output burden. So output burden means the output cable, the external burden, that what we are putting on the CT. So we are putting this cable and we are putting the meter. So that burden we need to calculate only. Okay, Villa, right now. So uh, follow this one. But I'm telling this one. Sometimes some Indian consultant have done this one. Contact resistance, no need to take Sales, no need to take the contact resistance. Which contact resistance? This is not circuit breaker, that contact resistance will come in circuit breaker contact. No need to take any contact resistance. 2 RL is not 3R. 2 RL, this RL is the 3. So, okay, let me correct this one. So, 3 into 2, right now, that Rasmita, that you are telling this one. Because this is 3 ohm for the one side, correct? Okay, so let me rewrite this one. Let me rewrite. So 3 into 2, 6 plus 0.6, so 6.06. In that case we need to take 10 VA, right, Rasmita? Now fine, this one. I is 2, this 2, RL is 3 ohm, 3 ohm. So 2 into 3 plus 0.6, 6 plus 0.6, 6.06. So now go to the standard available rating, so we can go with the 10 VA. Right, so there is some fine tuning here because we have not taken two factor here. That is the one reason. Okay, thank you, Rasmita, to point this mistake here. Okay, so yeah, burden is clear for everyone. I think so. I think so, right? Please let me know. Okay, so let us go to the next. I think this you understood. Let us go to the next parameters. That is the instrument security factor, ISF. Yeah, thank you, Amit. ISF. That is so. What is the ISF? Let me go. Let me take any this here. The CT rating plate. We can see here. This ratio is done. Burden is done. Accuracy class is done. This is the serial number of the manufacturer. Manufacturers the Excel automation. So no need to consider the EA tape. Okay. ILV, IS, I'll come on the ILV later on. IS is the Indian standard. So in India, we follow 2705 as the CT standard. But in international, we follow the IEC 61869. So we are discussing based on the IEC standard, not the Indian standard. But yes, IS is 2705. Frequency 50 and 60 Hz, that's fine. And here this one parameters, this is ISF and less than 5. So what is this parameters and why we should mention here, and what is the significance in a layman language? Yes, anyone have idea about this ISF less than 5? So what is the meaning of ISF? Okay, so let me tell that is the yes, that is the instrument safety factor or security factor. And in IEC the ISF is written as SF only. Safety factor are the factor of the safety. Instrument security factor, ISF. What does it mean? What is the basic significance of the ISF? We know the current transformation principle. The current transformation principle is what? Whenever the whenever the current flowing in the primary, this suppose I'm taking 200 by 5 ampere CT, and we know that CT work on this principle of N1 I1 is equals to N2 I2. So N1 N2 is the number of turns, so that is constant. So I1 is directly proportional to I2. It means when the 200 current is flowing, then secondary side 5 ampere current will come. And suppose any fault happens here. Let me put the fault. Suppose any fault happens here. Any line to ground fault happens, or any phase to phase fault happens in the circuit. So what will happen? In place of the full load current, the fault current will flow. Suppose the fault current is flowing 10 kilo ampere. My fault current is flowing 10 kilo ampere. So what will happen? It means how much time current is flowing. Suppose this is 20 kilo ampere. In that case, how much time? 100 more time right now. So 100 times more current is flowing in the primary side. So what will happen? At the secondary side, the current will come 100 times. We again have to multiply it, right? So it will come 500 ampere. So what will happen? What will happen? This connected burden, this connected instrument, and plus this cable is 4 square mm, and this connected instrument is designed for the 1 ampere. And as CT comes in two ratings, secondary side 1 ampere or the 5 ampere, so they can max to max they can bear up to 5 ampere. Let us see how much. Let me go to this energy meter, and let us see. Okay, 20 times for 1 second overload withstand voltage and the current. So 20 times they can withstand. Okay, that is fine. And if we say cable, so cable is 4 ampere only, so they cannot 4 square mm only, so they cannot carry the 500 ampere current, right? So what will happen at the this instrument security factor at the normal case no any significance, but when the fault occurs, so at the secondary side the fault current will go, and this instrument designed for the 1 ampere, and this cable is 4 square, so very minimum very small size cable we have taken. So at the secondary side, if 500 ampere current is flowing, so this cable will damage at the event of the fault. At the same time, this multifunction meter energy meter will also damage. So so what we want to to protect my instrument, plus to protect my connected cables, what is required that when the fault happens, then this CT should saturate. Then this CT should saturate, but not immediately. They not immediately means not on the every current. How much times current they can produce. So if we are taking IS of 5, it means they will reproduce, and they will transfer secondary side max to max 5 times of the current. And after the 5 times of the current, the CT particular core, because in CT we have many cores, so particular core, not all the CT, this particular metering core will saturate. And when any core saturate, then they do not have any excitations. It means they do not have any excitations, means output will be constant or output will be zero. In that case, when my core is saturated and not producing any output at the secondary side, so at the event of the fault, my connected cables plus the connected instrument will be safe and it will not damage. So instrument security factor is the factor of the security. If we are taking 5, it means 5 times they will produce, and after that the core will go into the saturation state, and that is also required in order to protect my connected instrument, because this energy meter or whatever the meters we are connecting here, that is not that is also costly equipment. And so in order to protect these cables and the energy meters, we need to put we require the saturations of the cores, and that we achieve with help of the this instrument security factors. 5 means they will allow 5 times of the current. So the I hope this instrument security factor, the basic meaning is clear. uh, the instrument security factor, or we can say the instrument safety factor in a layman language, instrument safety factor. Okay, and they have significance at the event of the fault. As per the IC, let us go to the IC. So all the discussions we will go with the IC only. So all my statement comes from the standards from the IC majorly. Let us go and see the factor of safety values what we can take, and why 5 they have taken here. So let us go to the output burden discussed. Uh, okay, resistive burden values, rated accuracy class discussed. Error also we discussed, and then yes, instrument security factor, and this is here instrument security factor. An instrument security factor may be specified. Standard values are FS5. As I said that IC do not take ISF, IC take FS. FS5 factor of safety 5, FS10 factor of safety 10. FS5 means 5 times current, FS10 means 10 times of current. The CT core will transmit secondary side, and after that the core will go into the saturation state, and when the core saturated, then CT will not, the particular core will not work, and at the event of the fault, and connected instrument and cable will be protected. I hope this is clear. So instrument security factor, this we we can understood by this also. ISF instrument security factor definitions specifies the current at which CT saturate, or we can say specifies the current at which CT core saturate, right? No, time is not because we do not allow time. We wanted that it should saturate as soon as possible. Okay, because if it is flowing, then the cable and instrument might be damaged for that time. So time means we can go that how much the withstand time of the cable and the instrument. Okay, how much time they can withstand, but the requirement is that it should saturate when the current is flowing more than 5 times or more than 10 times. Okay, yes. So definitions, there is no any limit there. We should, like when the city, when the current is flowing more than that limit, it should go into saturation state. Yeah, so the definition, this ISF specifies the current at which CT goes saturate, that is the definitions. Should be low or should be high? Yes, it should be low, correct, because it is high, then high amount of fault current will go on the CT secondary side, and that is not required, so it should be low. Significance, safety of the devices connected at the CT secondary side in event of the fault, that is the significance. Typical available values as per the IC 61869, 5 and 10, and generally we go with the 5. So ISF always we go with the 5. So I hope this every time ISF will be mentioned, every time it will be mentioned. If we take the metering CT nameplate, okay, every time it will, I will show you some rating the nameplate. Okay, the first nameplate that we can see here, this is the one nameplate, and you can see the ISF is mentioned. This is my LT system. Okay, let me ask what is the ILV. What is the ILV? Actually, what happens every time? No need to replace. Every time no need to replace. But yes, if it is not working properly after 2 or 3 times, then we have to replace that CT particular core. Okay. But what happens? Uh, uh, Even though we have the release, we have the protective release, and the whenever the fault will happen, the relay will issue the trip command to the CT, and CT will clear the fault. Sorry, it will give the relay will give trip command to circuit breaker, and circuit breaker will clear the fault. But suppose circuit breaker is not able to clear the fault, and the fault is persisting, it is available in the system, then the core may saturate. And suppose 2 or 3 times like that, the frequently core is saturating, then they like malfunctioning they can do. Okay, this one there. Okay, so this is the one rating plate. Okay, let me ask one point. What is the meaning of ILB here? Then we go to the next rating plate. Then we will go to the next other rating plate. Yeah, quickly, yeah, because insulation level voltage, correct. That is the meaning of the ILB. 0.66 means oblique 3 kilo voltage means because the system is LT. So for that, the 0.66. So what is 0.66? This one is what, and this one is what? Please come fast, yeah. Do not take time. I need to show some other nameplate of city also. 0.66 and 3 is what? In the insulation level voltage, what parameters we include? These are in the module number 1 we discussed this one, no? In the module number 1 we discussed this one. So that is why I'm asking, otherwise I will not ask. Uh, in the module this insulation level voltage, and we know that insulation level voltage three voltage we take: the power frequency over voltage, lightning lightning impulse over voltage, and switching impulse over voltage, right? And we know that switching impulse over voltage applicable for greater than 220 kilovoltage, and up to 220 kilovoltage this two is applicable: power frequency and the lighting impulse. So I think if 0.66, this might be power frequency, and this might be lighting impulse. I think so. I'm not clear, but I think so, because this two is the power frequency and this might be the lightning impulse. Okay, then 0.66 is what? This is 0.66. It might be then over voltage. Over voltage means power frequency over voltage. Uh, Power frequency over voltage means 415 right now. This is my 415 voltage CT. So it means 660 voltage continuously they can withstand. So the 660 is not the power frequency in that case. Let me 660 it, then it is the maximum continuous over voltage. Max, yes, correct, Salis. Could be max continuous voltage, maximum continuous over voltage, and 3 kilovoltage is the power frequency over voltage. Yes, because NLT lighting is not applicable, that is why 3 kilovoltage is the power frequency over voltage. Now it is fine, right? Raghunath, it is fine right now. Okay, IS the Indian standard 2705 frequency 50 we can apply. ISF is discussed. Now we discuss in the metering CT, we discuss the CT this calculations. We discuss this calculations. We discuss about this selection based on the applications, and we discuss about this selection based on the applications. So let us metering core CT. Let us exercise with the two different applications, and let me show you some rating plate. So metering core CT is now done from my side, and now let me show you some CT rating plate for the metering core CT, and we can identify CT instrument. Okay, nameplate. Yeah, that nameplate we can see. Okay, this is Maru make CT. Maru is the Indian manufacturer that manufacture the CT. Maru. Let us try to understand this CT rating plate. Okay, current transformer with the SS is what? What is SS? This is the CT rating plate. This is 220 kilovolt CT rating plate. So as a engineer, as a design engineer, or as electrical engineer, when we work in substations switchyard is for the 220 kilovoltage, we should this rating plate we see at the site also on each equipment. So we should understand this electrical terms. Yes, correct. The with as stillness is still below. What? Why the below is required? What is below, and why this is required? Why not without SS below? And not the yeah, that we can say airtight Shivam, but actually below means at top. Yes, because what happens in the city, we fill the oil, right? Oil filled city. Oil is the insulating oil. Insulating oil. So what will happen when the overload? Yes, yes, correct. So at the time of the overcurrent or heat, the oil will expand. So oil will expand their volume. So if we do not provide the bellow, when the oil is expanding their volume, the CT may damage. So in order to balance this oil expansion at the event of the heat, this bellow is balance the pressure and CT will not damage. So that is why oil filled CT is provided with the bellow. That is to balance the oil expansion or contractions, both we can say, and that keep air that keep oil tight. Right now I think that's clear, Shivam. Raghunath, anyone? Okay, yes, just trying to understand whatever the technical terms given in the rating plate. Made to IS2705 because that is the Indian manufacturer, that is why they have put IS2705. But if this is international, then it should be IEC 61869. Rated dynamic current. What is the meaning of rated dynamic current? I'm just referring the rating nameplate of the current transformer. Okay, so please be active. If anything you are not clear, you say no, I'll come on that. Because since you all see this rate nameplate in the substation at the site on the equipment, so I think that you have idea about these terminologies. What is the meaning of rated dynamic current? Rated dynamic current means and that is given 100 kiloampere. It means my fault current for the 220 kilovoltage is 40 kiloampere, as we can see here. My fault current STC short time rating, short circuit rating we can say, and that is 40 kiloampere. So dynamic current is 2.5 times of the rated short time current. So that is the thumb rule. So 40 multiplied by 2.5, 2.5 is a thumb rule. And why 2.5 we take, I will explain in the my next weekend in my circuit breaker class, where I will calculate the making capacity of circuit breaker. Then I will explain the 2.5 factor. Okay, so yes, DC component plus the peak value. Okay, so 2 comes to here. DC component plus the peak value. So 2.5, so 40 multiplied by 2.5, it will come 100, and that is given here. So everywhere, whenever you see any dynamic current, it means the dynamic current is the peak current first of all, and peak current we calculate based on the, and this is the RMS current, and in the RMS current we multiply by 2.5, and that give the peak current or that give the dynamic current. So that is the thumb rule that you can remember every time, and everywhere it is applicable. Okay, insulation level already discussed in module number 1, for 220 kilo voltage, this is the insulation level. Okay, power frequency withstand voltage for secondary winding 5 kilo voltage for 1 minute, and that is okay because 3 kilo voltage required at the, because we know that, and the LTV take 3 kilo kV right now, as you said here, in LTV take 3 kilo voltage, 3 kilo voltage, 3 kV. They are offering the 5 kV, so that 5 kV is also correct. It is they are providing 2 kV more than my requirement. So secondary side, this I'll come on that, Siddharth. It means how much the peak current this equipment can handle. That is the significance of rated dynamic current. Okay, Siddharth. How much the peak short circuit current they can withstand. That is the significance of the dynamic current. And this peak current have the two component. One is the peak 0.2 and plus DC component also they have. So 2.5 factor I will calculate and then will show you. But yeah, that is the significance, that how much peak short circuit current they can withstand this equipment without failure. That is why dynamic current is also required on the rating plate, not only the RMS current. Okay, so that okay. This 5 kilovoltage is also clear to everyone. Let us try to understand one rate nameplate of the CT. Okay, yeah. So then nominal system voltage 220 kilovoltage. Yes, nominal is okay. Nominal is okay, right? Rated voltage 245 kV. That rated voltage is also okay. Okay, I'll keep your chat box here so that I will see if any query. So highest okay now, for circuit system voltage okay, rated frequency 50 Hz. Now as we see, as I said in beginning, that we use multi-core CT. So here we have 5 core: core 1, core 2, core 3, core 4 and core 5, and that we can see here also we are using the 5 number of the core. One is the primary common and 1 core, 2 core, 3, 4, 5. But yeah, we using 6 core. We'll come on that tan delta terminal. We'll come on that tan delta. So basically 5 core we are using for the CT, and this is this tan delta terminal and link we are using for the tan delta testing of the CT insulator. Okay, that is for the tan delta testing of the insulator. Will come on. I will try to discuss tomorrow what is the tan delta test. Then it will be clear. This terminal will be clear. But 5 core CT, yeah. Primary and we take multi-core multi-ratio, as you can see the multi-ratio CT. This three core is multi-ratio and this 2 core is fixed 900 only. A secondary current is 1 ampere. That is done. Now let us take the metering core. So core is the protection core, PS core, right? Core 1 is the PS core. PS core till we have not discussed, so core 1 will not go. Core 2 again PS accuracy class, PS class, so that not discuss, that we discuss tomorrow. So not discuss. Yes, core 3 metering core. Because as I said that for the CT sizing we have to do the core sizing. So my core 3 sizing I have done. So core 3 sizing, this core 3 sizing. This is my secondary terminal. So we have 3 tappings: 3S1, 3S2, 3S3, 3 tappings. So if I connect my meters between the this 3S1 and 3S2, between 3S1 3S2, then they will measure the 450 by 1 ampere current, and if we connect between 3S1 and 3S3, then they will measure the 900 by 1 ampere current. Okay, because we are cutting the number of turns, so that is why their this current ratio measurement is half. That is the reason. Okay, we are taking the tappings in between of the windings. So this one, so this secondary terminal is now rated burden in VA. So 20 VA we have mentioned here, but I think what VA required, that VA calculations we have done. How to calculate this 20 VA, that calculations we have done right now. How to calculate this is already we have done discuss. Accuracy class 0.2 S, and as I said that in substations we take 0.2 S class, they have taken the 0.2 S class CT. So that is also done. ALF stand for the accuracy limit factor. I'll come ALF later on, but ISF we have discussed at present. So ISF is instrument security factor, and that is less than 0.5. So CTR, this parameters, this four parameters, all we have discussed. Knee point voltage and other parameters is not applicable for the metering core. That is why we have not discussed the other parameters. Okay. Year of manufacturing 19, serial number. This rated continuous thermal current 120% of rated primary current, that they can 20% more current they can also withstand. They can also measure without any thermal or heating. Okay, that is the meaning of this. Material of nameplate aluminum and anodized. Thickness of nameplate is 1.2 millimeter. Serial number shall be engraved before the dispatch. Letter height, whatever the letter height that you are seeing, that is 2.5 mm, and thickness of letter is 0.3 mm. That is given by the CT manufacturer. Okay. Creepage distance, that not discussed, but that discuss. I'll try to discuss that tomorrow at the next class. Creepage distance. Oil quantity in liters. So 225 liter oil we are putting in this CT. Total weight of CT 950 kilogram. I think that is the rating plate. So you ask who asked me about the rating plate here. Let me go to let me who asked me the okay Amit. I will show you the SS below picture. I will show you. Don't worry. We have one session how to review the CT vendor drawing. So at the time of the CT vendor physical drawing review, I will show you the below. Okay, Amit. So I address your query here. Below means yes, below comes on the top and I don't know who asked me about the rating rate. Yeah, Bella, you ask me, now I address your query. Yes, okay. So every time this rating is given in the okay, yeah. So let us go to the next CT core selection and their calculations. See, first of all, at this Pandey, the manufacturer will not calculate the VA rating. The VA rating we have to provide to the manufacturer. Okay, this CT rating plate we have taken here, but before taking the CT, the sizing calculations we have done, and these parameters we have to provide at the time of the purchase. These four parameters, whatever we discussed, these four parameters we have to provide to the CT manufacturer, and based on all by four parameters they will make the CT and they will offer us the CT rating plate. So first of all, this Pandey, these parameters manufacturer will not calculate. This as a engineer we have to calculate. Clear? Your point is, and that's what we are discussing here. That's what we are discussing here. How to calculate, and oh, and after the calculations we will make the inquiry specifications, and in the inquiry specifications we will write all these parameters, and that we will give to the manufacturer, and the manufacturer will give us the drawings, technical data sheet and rating plate that we have to approve, and after the approval they will do the manufacturing, and after the manufacturing we have to do the FAT, and after the FAT we have to issue the dispatch clearances, and then the manufacturer will dispatch the CT to the site, and at the site we have to do the site testing, and after the testing we have to charge the CT. Okay, this Pandey, that is the process, overall process. So we are discussing the calculations. I think if anyone any other have this kind of the query, so they can understand. This is clear to everyone. This is not only for you, this one. And that is why we are doing the selection sizing calculations. Okay, let us come on the next CT core metering. So metering done, let us come on the protection. Let us come on the protection uh, core selection and the sizing calculations. So as we discussed yesterday, that protection again divided many type. So okay, that is my conclusion. Okay, that is the another. So let us come to the protection CT, and let us try to understand between the protection CT core and the metering CT core. What the difference between two? Metering CT core, yes, we have discussed, and in the CT sizing we do the basically core sizing. Basically we do the different core sizing. Metering core sizing we have discussed. Let us go to the protection core sizing, and let us try to understand the difference between the metering core and the protection core. Yeah, accuracy is the one factor. In that case, in that case, the required power, the required power city will not able to generate, Raghunath? That is the same. You can see that you are taking the 2 MVA transformer and you are putting 3 MVA transformer. So what will happen? Same you can take here also. 20 or 10 VA city we are taking means they can produce 10 VA power. Now you are putting 20 VA power, 20 VA burden. So what will happen? You are increasing the resistance, then what will they will not able to handle that burden. The city will not able to handle that burden. Okay, Raghunath. Okay, so let us try to understand the difference between the metering core and the protection city core. Yeah, accuracy is the one different. Okay, so and other than accuracy, what the other difference we have? The difference between the protection and the metering core, metering city core, as current transformer are used for metering and protection purpose, metering of the current and protection based on the current purpose. However, there is a very important difference between the metering city and the protection city. Metering city is so designed, metering city core, if I am telling more specific, the metering city core is so designed that in case of the fault, it will saturate and thus save the instrument connected to its secondary from damage due to excessive current. Whereas a protective city core is designed to faithfully reproduce the largest fault current to secondary site at event of the fault without the saturations, or we can say uh, uh, without operation of the relay. Means the significance of protective CT core is that they should not saturate, means they are going to saturate at the 5 times, but it will not saturate on the low amount of the current, it will saturate on the high amount of the current, the protective CT. And the main objective of the protective CT is to faithfully reproduce the largest fault current to the secondary site at the event of the fault. That is the two difference. Means when the fault occurring, then we want at the very amount of the fault current we want to saturate this metering core, but we do not want to saturate this protective CT core, and we want that it should faithfully or correctly reproduce the fault current on the CT secondary side without any pre-saturation. Yes, they can saturate, but not the less amount of the fault current. They can saturate on the very high amount of the fault current. Saturate city means the core saturate, and once any magnetic material, any material saturate, then they will not generate the flux, and when they will not generate the flux, then there will be no any transformations right now, because we know that this all the transfer work on the induction principle and the fluxing, the flux produce when the uh, current voltage passing. So when this material is saturated, then they will not generate the flux and it will not work. Okay, Mehul, clear? That is the magnetic materials now. That if this is with the flux, they will not. Okay, so coming back, I hope the difference between the metering CT and the production CT is clear. So let us try to understand about the protection CT, and as we discuss overall type of the CT, so measuring CT, now we come on the protection CT. This protection CT again as per the Indian standard PNPS class CT, PNPS class CT core, whereas as per the IC the protection CT core is this much more types PX. This PS and PX is the same. TPS, TPX, TPY and TPZ, and this P and this P is the same. This P and PS is the same as P and PX, but the TPS, TPY and X, Y and Z, that also we use. Where we use this TPX as X, Y and Z, that you can go to IC 61869, and in the IC 61869 you can refer and that you can understand that where we use this X, Y and Z CT. In the IC this TPX, Y and Z is mentioned and their definition is also mentioned. So you can go through and you can see this TPXY and Z. You can refer and you can see here Y and Z. So you, from the IC you can refer for this X, Y and Z. In generally, we use the P and PX class CT are as per the IC we can say in generally usually we use the P and PX class CT. So let us discuss the calculations what we use mostly P and PX class CT. So before going on the P and PX class CT, we should understand the difference between P and PX class CT core. What the difference in P and PX class CT core, and where we go with the P class CT core and where we should go with the PX class CT core. And same as the point 2S, point 2 and point 2S, S stand for the special. So protection special we can say like that, and the normal protection we can say the P is the normal protections. And here we have the protection special CT core. So let us try to understand uh, some difference application wise between the P and PX class CT core. So as two type of protections class CT core usually use majorly P and PX for the, and let us understand where we go P, where as an engineer we should use P class CT core and where we should use the PX class CT core. So for the low voltage, medium voltage and high voltage if I am telling that I am telling 11 kilovoltage and 33 kilovoltage. Okay, in generally are we can say usually the overcurrent as phase to phase fault happens or any phase to earth fault happens, overcurrent and earth fault protective relays used. Overcurrent and earth fault protective relays used for this voltage level. Therefore, for these protection relays, for the overcurrent and earth fault protection relays, the P class or P type CT core is required. So that is the one statement. I hope this is clear. This statement is clear. Yeah. So P class CT core used for the protection purpose of LT, MV, HT feeders, motors, and a small distribution transformer, a small transformer we can say. Whereas for the extra high voltage and ultra high voltage system, generally we have two set of the protections from 66 to 132 kilovoltage main protection plus the backup protection. And backup protections we take over current and earth fault type protection, and for that we use P class CT. And above 132 kilovoltage we take two set of the main protections. Backup protections we do not use. We have two set of main protection, and both main protection operate simultaneously, and it give tripping command to trip coil of the circuit breaker, and circuit breaker have two trip coil 1 from the main protection 1 relay and trip coil 2 of circuit breaker from the main protection 2 of the relay. Main protection is main protection is the closed loop or the particular zone protection, or we can say it is called as the unit protection. So for the closed loop or zone protection relay, the required CT should be highly accurate, and P class CT core have large error, so it's not perfectly suitable for the closed loop or zone protection or unit protection. Therefore, for main protection in case of the extra and ultra high voltage, for the main protections in extra high voltage system, PX class CT core use, and that PX class CT have very less error compared to P class CT core. So what we understood here, let us summarize this discussion. What we discussed now, after the metering core sizing, we are going for the protection core sizing of the CT, and we discussed that CT protection core, CT protection is two type of the CT core, two type of the CT core we use. One is the P class and second is the PS, special protection, or as per IC this is expressed in the PX. P class CT we use for the low voltage, medium voltage, high voltage, system, 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 and for all these systems we use the overcurrent and the earth fault relay and the earth fault relay. So for this relay we take P class CT. Okay, and when it comes to the extra high voltage, I am telling extra high voltage means I am telling from 66 kilovoltage to 132 kilovoltage. In that case we have two set of the protection. One is the main protection plus we have the backup protection. So for the main protection we use the PX class CT core, and for the backup protection, since the backup is will work when the main protections fail to work, then the backup protection work. And the backup protections we take the overcurrent protection and the earth fault protection. So for this protective release, same as the this medium high voltage system, we take the P class CT. So up to this voltage, we use both PX and P class CT core. PX for the main protection and P is the backup protection. But when it comes to the this ultra high voltage, I mean to say when it comes to more than when it comes to 220 kilovoltage or 380 kilovoltage and 400 kilovoltage, in that case we do not use the backup protections. For the in main we use the two main protections, main 1 and main 2, and due to that reason both required the PX class CT. So in that in this voltage level we do not use the overcurrent and earth fault, and therefore the P class CT we do not use. PX and PS class CT. So different, this is the one selection of the P and PS class CT based on the voltage level that we select. Okay, P class CT have the P class CT have the higher error, and PX class CT have very less error. I think this is around 1% of the error, and they have 5%, 10%, 15% like that. We'll go on the P class CT selection, the sizing calculation that we will see the type of the error. But here this have only 1% of the error, so that is less error. And so other in a other way we can define the difference between P and PS class CT, that P class CT we use for the overcurrent and earth fault relay, for overcurrent and earth fault relays, protection relays. Okay, a relay means what? Because we take the breaker and we put the CT, and this one CT is for the metering purpose that we have done, and second core we are using, and it provide output to the relay. And if more current is flowing than the rated current, in that case the relay will pick up, this relay will pick up, and this relay will give tripping command to the in to this circuit breaker. So at the event of the fault, the system will be isolated. So we are discussing this CT, but this CT is we are discussing with respect to the relays. So for the overcurrent and fault relay, we take the P class CT, P type CT or P class CT. But when it comes to the to any closed loop protection or zone protection or unit protection, in that case we use the PX class CT core. What I mean to say the closed loop or the zone or the unit protection, it means let me show you first of all some sketch of the closed zone or unit protection. After that we will discuss what is the meaning in the layman language. So this is a electrical power system network that we can see here, and let us try to understand the zone of the protections. Now in the electrical power system network we have the generator, and this generator generates the power and we feed to the bus, and after that we have transformer. We have the transformer here, so please take this one as the transformer, and we step up the voltage and then we feed to the bus, or uh, uh, with the help of the bus we feed to the transmission grid. So so now what is my uh, zone here, production zone here? What is my zone of production here? So we have many zone in a power system network. We have many zone of production. What is the generator zone? What is mean of generator zone? It means if any fault happens in the transmission line, in that case this circuit breaker should not operate. Only the breaker that in the transmission zone, this breaker and this breaker, this should operate. Other Any other zone, breaker or relay should not operate. If any fault occurs in this particular zone, in that case this relay will operate. So my one is my zone, generator zone. Second, this one is my bus zone, and we do the overlapping various zone. For a typical power system are shown in figure. It can be seen that the adjacent zone overlap, otherwise there could be some portion which is left out. So that is why overlapping is required. But uh, in the overlapping we can set the priorities also. Okay, so zone, this is my generator zone, then this is my bus zone, and here my transformer zone, and this is my bus, again my bus zone, and here my transmission line zone, and again transformer, generator, circuit breaker. So this is in the power system network. So first of all, this type peak class city we take for low voltage, medium voltage, high system. But when we go to the grid, when we go for the extra ultra high voltage, and when we go to the power system, in that case this peak class city we use only for the backup protections, and the main protection is my px class ct, because they have the better, they have the less, they have the better accuracy and less error compared to the p class ct. And with help of the px class ct we use for any closed zone, closed loop protection, zone protection, and the unit protections. Okay. Yes, correct, Raghunath. Your statement is perfect. Protection whose boundary can be defined is a unit protection, and boundary cannot be defined, it is non-unit protections. And that is why my overcurrent is the non-unit protection, because we do not define any boundary, uh, and that is the non-unit protections. And the unit protections we define the boundary. And as we discussed here, we are defining the boundary of the protections. It means if any fault occurs beyond that boundary, so that zone relay should not operate. And due to that, we get the reliability, and due to that, we can easily find out the fault in the grid. Okay, that is the advantage. Okay, so yeah, thank you, uh, Ganesh. So coming back, yeah, selectivity. That is the point. That we have the option of the selectivity. Okay, if we have the zone protection. So I think that is clear. The px and the p class cities. So when we come to the substations, so in the substations we have the following type of the zone, or following type of the circuit, or following type of the unit protection required. We have the transmission line, incoming or outgoing. So uh, this one is one transmission line is my one zone of protection. We have the transformer, that is my second zone of the protection. We have the bus bar. So for that is the production. So all for the transmission line, for the transformer, for the common electrical bus bar, we go for the px class city core. Okay, so the basically the px class city core comes in the substation and in the power system network. And this p class city core comes for the low voltage, medium voltage, high voltage systems up to 33 kV or 11 kilo voltage in generally, that we can say. Okay, so we'll go to the PS classicity selection and sizing calculations in tomorrow session, because that is again 2 hours session. Okay, so let us discuss about peak class city today. So if we talk about the peak class city, so same as the metering core city, I hope you understood the difference between P and PS class city and their applications and the selection based on the voltage also, right? So same as the metering core city, we need to specify the parameters for the peak class city core also. So for the peak class city core, again 4 parameters we need to specify for the selection. Okay, one is the CTR, current transformation ratio. This is the same as the for the metering core we discussed. Same principle apply here. Second parameters we need to specify, that is the we can see second parameter is the burden in terms of the VA, or we can say the output power required from the CT, that VA. Same as we discussed for the metering code, same principle applied here. Third parameters in the metering core, we have taken the accuracy class zero point 0.2, zero point 0.2s, 0.5, 0.5s, 1, so on. But in that peak class city, the accuracy class as per the IEC 61869, as per the IC 61869, we need to select. Let us go to the 61869 and let us see type of the production accuracy class. So going back to the again 61869, and let us try to understand for the P class city core what is the available protection uh, class available for the P type of the core. So coming to the IEC standard, and going to the this okay, please also you check in if you need. Okay, this is the metering core okay, so metering core, yes, protective current transformer, and general means PX, you can see defining current defining, so PX TPY, that you can see here. For the transient case we go with the TPX TPY and TPZ. Okay, yeah, ALF will go, yes, correct. Standard accuracy class, two standard accuracy class is available. I'll come on that, Mehul. And again request, please follow me. I will not left any point without discussion. That I promise. Okay, and my course time is 3.5. It may go if 4 month, 4.5 month, 5 month. I don't have any issue. But my point that I will discuss each and everything that we use in our project or in job. Okay. Okay, so coming back to the standard accuracy class, So as per the IEC, the standard accuracy class for productive current transformer are 5P and 10P. Means in metering CT we have many point 0.1, point 0.2, point 0.2s, point 0.5, point 0.5s, and class 1. But when it comes to product protection CT code, then we have only two options. We can go 5P or we can go 10P. What is mean of 5P and what is mean of 10P here? 5P means P stand for the protection, no doubt in that, and 5 stand for the 5 percentage of the error during the current transformation from primary to the secondary. 10 stand same, 10 percentage of the error during the current transformations. That is the meaning of 5 and 10. 10 means 10 percentage of error, that is huge error. So that is why in generally 10p we do not take, or we do not consider, we do not select to use in the industry until unless any client is asking specifically in that. Otherwise 10 we do not take. Same as metering, 3 and 5 we do not take. So now one option is left. Yes, that we can say at the time of the fault current or at the time of the overcurrent. Anyone you can say. Okay. Yeah. So 5% of the error at the time of the overload or at the time of the transformation. That is not the fault current actually. That is during the transformation. Okay. This transformation may be in the continuous loading also, not the fault current loading. Okay, Mehul. So please correct your understanding. So 5 means the so now let me come back to the acoustic class. As per 669, 5 and 10p available. P stand for the protection, 5 stand for the 5% error between the CTR current drop. So 10 we do not take, 5 we take. So 5p is the standard we can see. Acoustic class CTR is done, we are done, same as the metering. Acoustic class 5p. Okay. Fourth parameters, in the metering we have taken instrument security factor, but when it comes to P, we do not take the instrument security factor. In place of the instrument security factor, we take the accuracy limit factor. Accuracy limit factor. What is the meaning of accuracy limit factor? Accuracy limit factor. A means the accuracy, that is fine. Limit factor means means uh, same as the ISF required at the time of the fault, at the event of the fault. Same ALF is required at the event of ALF is significance at the event of the fault. Okay, accuracy limit factor ALF, the fourth parameters ALF accuracy limit factor at the event of the fault. At event of fault, this is used. Okay, at event of the fault means accuracy limit factor, that up to what up to what limit up to what limit your accuracy is guaranteed, up to what limit in the current transformation your accuracy is guaranteed by the CT manufacturer, or what you required as a engineer, what you required, that how much should be accuracy should be guaranteed by the manufacturer at the event of the fault. Okay, Mehul? Correct. See, we can say like that also. Factor up to which accuracy is limited, or Shivam, we can say like that. Accuracy is guaranteed by the manufacturer. Okay, Shivam, we can read guaranteed by the manufacturer. Beyond that limit, the accuracy is not guaranteed by the manufacturer. This accuracy may increase to any times, to any value that is not tested at the factory. Okay. Now, next, what is the parameters? What are the, as in ISF 5 and 10, two value available. So similarly, ISF, what is the value available as per the IC? So please revisit to ALF, to the IC, and let us see the available value. So class P protective current transformer standard accuracy limit factor ALF 5, 10, 15, and 20 and 30. So again, 5 option is available. 5, 10, 15, 20 and 30. 5 option as per IC available. As a design engineer, we have to select out of this 5 options. 5 means what? Means 5 times. Let me take the snapshot so that we can discuss here. Okay, 5, first of all, this we can also write. 5 means 5 means 5 means 5 times. So this is times of what? Times of rated current. Times of rated current. If means if I am telling ALF 5, it means if suppose my CT rated current is 200 by 1 ampere, then 5 multiplied by 200 up to 1000 ampere, the 5 percentage is error is guaranteed. And what we do actually, this both parameters, the accuracy class and the ALF, this both parameters 5p and ALF as per the IC 5, 10, 15, 20 and 30 available. So what we do basically, as a conventional practice, we both parameters, in place of specify differently, we combine both parameters. and in a combination we express, means we combine the Cl and the ALF, means ALF means Cl is 5p, right? 5p, and ALF is what we selected, that we specify here. Specify combined means 5p and ALF means 5p. If I select ALF 5, so then it will be 5p 5. If I select ALF 10, it means 5p 10. If I select ALF 15, then it means 5p 15. Similarly, we can say the 5p 20. So if I'm telling 5p 20, it means 5p 20 is what? 5p is my protection class, accuracy class means 5% of the current. 20 means what? 20 means accuracy limit factor. This 20 is this one, limit factor. It means what? 20 times of the rated current. It means, suppose my current is 200, so 200 multiplied by 20, how much it will come? 4000, right? So up to 4000 ampere, the 5% of the error is guaranteed by the CT manufacturer. Beyond 4000 ampere, this error may increase. What value will increase? That is not done. That is not guaranteed by the manufacturer. Okay, so that is the protection class CT. Four parameters we have to specify. CTR calculation, same calculations as we have performed for the metering code. Burden, same calculations as we perform for the metering code. CL, we have selection. ALF, selection out of four parameters. And in generally, what value we select? Suppose I am taking 5p5. 5p5. So what will happen? Means the only 5 times current this error is specified, and that is very less current, 5 times of the current. So generally 5 we do not generally not consider. What we consider, we take 10, 15, 20 or 30. Out of this 4 we take 30, means what? 30 times current we can go, and it means 30, it is better CT. Okay, 30 times of the CT we can go, are guaranteed by the manufacturer. Then obviously cost is also vary or increase. 15 means 15 time of the CT is guaranteed. 20 means 20 times. And what I have seen to use in the industry, that 99% case I have seen that generally selected ALF is 20. And so based on this normal engineering practices, 20 select. So the P class CT is expressed as the 5p20. Okay, 5p is 5 is the 5% of the error. P stand for the protection class CT. 20 stand for the accuracy limit factor ALF. Okay, 20 means 20 up to 20 times of the rated current. 5% of the error is guaranteed by the manufacturer, or you wanted to guarantee by the manufacturer. Okay, 5p20. Right. So these four parameters we have to specify and we have to select or we have to calculate. I hope this P class CT is clear, but same principle we do not apply for the PS class CT. No, PS class CT is altogether different, and PS class CT is for the generating plant, for the substation, for the transmission line. The PX class CT we use. So let us discuss the PX class CT in a more depth, in a more detail, and we keep the separate two verses on the PX class CT: selection and calculation. Okay, so I hope so far everyone is clear. And so what we discussed till uh, now, we discuss the CT sizing for the LT and medium voltage and high voltage system. So let us see some high voltage system drawing also. Extra high voltage, ultra high voltage we will discuss tomorrow. Can I have some SLD? Okay, let us take one SLD. Yes, that just give 5 minutes. We will continue for, because PX I do not want to discuss today because that is very important. Okay, so we'll discuss tomorrow. Okay, P class CT for the medium voltage, high voltage for the protections we use. So that just I wanted to show some reference SLD and use of the peak capacity. Okay, that. So coming back, so here I think can we zoom this? This is a SLD, that is essentially for the National Aluminium Company. EIL is the consultant. Okay, and now this is a SLD for the new service station, but that rating is how much? 11 kilovoltage. This test is not so much clear. 11 kilovoltage switch board. So this 11 kilovoltage system here. Okay, and now you can see this is the VCB, and here we use CT for the protection purpose. Here this drawing is not very much clear, so the relay is not clear here, but yeah, 200 by 5, 15 VA. So this 15 VA we can calculate based on the cable and this burden. Class 5P10. Okay, so this class is we need to select and we have to write here. 10 we have taken, we have put here, but 20 is better that you can go 20 because 20 times you can take the guarantee. Okay, so this is all is the 6.6 kilovoltage switch yard, and then incomer feeder, transformer rating 2.5 MVA, 6.9 kilovoltage, 630 voltage VCB, and 350 by 5 ampere CT, 15 VA, 5P10. So I think this CT core we can do the selection right now. We can do the sizing. We can take the CT power transformer rating 2.5 MVA, 6.9 is the voltage, so we can calculate the current. So based on that, this CTR we can decide. 15 VA burden we can calculate based on this cable burden plus based on this relay burden. This 15 VA burden we can calculate, and class is just the selection, not the calculations. And we have selected 5P10 means 5% error at the 10 times of the current. But please take 5P20, it will be more better. Yes, 10 is given here, so I think we understood what is the meaning of 10. Okay, so that is some medium voltage or low voltage high voltage system SLT, where we take this protection peak classicity, 5 peak classicity. Okay, so let us continue the remaining discussion of the CT PX tomorrow. So tomorrow we are going to discuss about the transmission line, differential distance, and transformer differential, this kind of the CT sizing calculation. Okay, so any query now we can discuss. So if no query, so we can saturate, then desaturate here, Mehul, what you can do. Yes, replace, that is the option. Yes, you need to replace that CT, purchase new CT. Okay, I don't know how to resaturate. Then in that case, you need to replace Ganesh. Okay, no option. You have to replace that. That is the option. I'm just kidding with the Mehul. Correct. Yes, Raghunath. Knee point voltage it comes into the PX. So that we'll discuss tomorrow. Okay, Raghunath. Yeah, tomorrow. Knee point voltage sizing calculations. Okay, so Silpa, for 2 CT core of burden 15 VA and 30 VA, two metering core. Okay, which physical design parameters in CT is affected to implement it? Physical design parameters. I'm not getting your actually query properly, Silpa. Can you elaborate more? What you are trying to say? Two core of two CT cores of burden 15 VA and 30 VA. So burden is different. Okay, Which physical design parameters? Actually, physical design parameters, Silpa, it is uh, take care by the city manufacturer that what physical change they are going to do. I think that how they required more power, so what they can take the more number of high resistance. I don't have, because this is taken care by the city manufacturer, Silpa. I'll discuss and come back to you if any. Actually, I'm not able to understand your query also properly, but I'll try to decode and will come back to you. Okay. Are you? If you can discuss, you can unmute so we can discuss on uh, verbally. Are you there, Silpa? Okay. BA burden is built by which physical parameters design in city. What may be? I'll check and then come back to you. Okay, I uh, type. Okay, let me allow. You can now unmute. Type of the conductor. Type of the conductor that they can take. Type. I don't think what the type of the conductors are in.
Yeah, I think because the type of conductor is different for protection and metering gas. Because for metering gas, it has to saturate quicker, and protection gas should not saturate. So the type of conductor and the I think the physical, that is the width of the conductor, that those things are different with regards to protection and metering gas. I think that will difference in series course just depends on not conductor.
Now they are asking Ganesh for the higher VA what the parameters.
Okay.
Uh, Asraj, because we have one manufacturer engineer also here. Let me check Asraj. I think they are the manufacturer engineer. Are you there?
So
Yeah,
I
Asraj,
have
you are there. You tell now, Asraj. Can you unmute? Okay, I'll check and then revert you. Okay, discuss with some manufacturer.
and I'm not clear on the query also that I asked. What will happen when the burden is more, the connected burden is more than the burden mentioned in the CT secondary. That is the CT nameplate.
Okay, Rana, that also because in that case, what will happen? They will not. What will happen? The core may saturate our.
Yeah, because when we were discussing, we were saying that what will happen in case of power transformer. But the difference between the power transformer and instrument transformer is, if power transformer, the load is high in the secondary, it can simply drop from the primary, right?
Mhm.
But the instrument transformer, whatever is in the primary, it is just replicating it in the secondary. So I don't know how we can draw from the primary again. So I am not clear on the concept. What will happen if the burden is high?
Yes. Yeah, I think the core may saturate. That is the one point that I can guess, Rana. But yeah, I'll take this point with some manufacturer. Okay.
Thank you.
And yeah, so as Raj, as per because he's one of the manufacturing engineer. So as per him, the material need to change. So that one point we can take Silpa at present. The material of the core. Okay, and other if any point comes, I will share with you. Yeah, Raghunath, yes, correct. Cross section of the conductors. We can increase the cross section of the conductors in that case. Yeah, Jayant. Because that is the one option we have, because we do not have many thing in the city. We have the conductors, the primary and secondary side. I think I got one some side picture also that is shared by Ganesh. I think you have shared right now. Ganesh, they have shared some side picture also. The in that I'll try to say in the group also. We have only the windings, so that with that winding conductor cross sections we can play.
So this one question.
Yes, Alice.
Yeah, refers to depending on voltage levels. For LV, you're not mentioning anything on the point two or point three years.
Actually, LV point two and because we discussed 2 points, Alice. One is the voltage based, and second is the application based.
Application based, right?
So
Yeah.
for the low voltage, if the application is for the energy metering,
Mhm.
in that case we can go with the point two S class city.
Okay. Okay. So there is no any such limitation in terms of
Yeah,
we
no
can't
limitation
select.
in terms of the voltage. Based on the applications we can take.
Yeah, okay. So in market it's available, right?
I think so, available. Okay, so we wind up today, and tomorrow we have a discussion for the protection special class city sizing calculation. Okay, so any feedback, anything that we should include, let me know. Tomorrow we can include, or if it is fine, so we can close. Okay, so good night all, and thanks for attendance.